We are on, let's see what slide we're on. We are on slide 38, 58. 20 more slides. Some of them will go quickly. One thing you need to learn about is aromatic hydrocarbons. Aromatic. We have covered.
Sorry.
Okay, we have covered alkenes pretty well. I'm going to mention polymerization real quickly. Polymerization. We are in the plastics age. I mean, look around you. This chair is plastic. Half of my car is plastic. The steering wheel, the bumpers, all kinds of stuff is plastic. I mean, this stuff, the markers are plastic. The Ziploc baggies, the milk cartons, the drinking bottles, plastic. The insulation that goes on the outside of homes, polystyrene, plastic. These are made from alkenes by polymerization. So, life without plastics: computers, cell phones, cars, clothing, nylon, polyester. All of these things are plastics. How are they made? They're made by polymerization. And I'm going to just mention this real quickly. If you got a bunch of R's around that molecule, but imagine that molecule up there being this molecule. That is ethene. Its common name is ethylene. And if you polymerize ethylene, you get polyethylene. And you get a multi-billion-dollar business selling Ziploc baggies. Polyethylene. If you take propene, or the common name would be propylene, and you polymerize it, you get polypropylene, and you got another billion-dollar industry making milk cartons and making Clorox jugs and plastic jugs that are mostly polyethylene or sometimes high-density polyethylene. All right, I'm going to just kind of go through this real quickly. So if I had this molecule, I'm not going to write the hydrogens. I don't think I will write the hydrogens. And I had another one next to it, and I had another one next to it. And we're going to polymerize them. I used to work for Dow Corning, and Dow Chemical, I mean, they're big in polyethylene. They make a lot of polyethylene. I regret getting out of Midland, Michigan without getting over to see how they did this. Because I could have gone over and just seen how they make polyethylene and blow it into big sheets and make it into Ziploc baggies and sell it for 30 cents or 50, 60 cents for a box of them. All right, so they get an initiator over here of some sort, a very reactive species, and it comes plowing into here, and it makes this. This one electron goes in there to make that bond, and this other electron goes right out here and makes that a reactive species, and it plows into this one and connects, and that one has a dot in the end, and it plows into the next one and it connects, and it plows into the next one and connects, and you get polyethylene. You get a lot of heat. You can melt the reactor doing this stuff. You have to do it slowly but surely because it gives off a lot of heat. And you can see whatever ends up with is probably going to have an even number of carbons in it because you're adding 2 at a time. 2, 4, 6, 8. Polyethylene. So what they would talk about is you have this monomer. This is your monomer, and they'll put an X down here, and X could be 1,000, 2,000, 3,000. of these units going along there. So if X was 1,000, the polymer, the polyethylene, would be 2,000 carbons long. You with me? And they would tune their reactor to make it the length they want to. The longer it gets, the higher the melting point would be, the stiffer it would become. So at a certain X, they have a nice flexible little bag. At another X, they might have a fairly stiff carton. They can make a carton out of it and it won't flop over, okay? Because it's not Ziploc baggy, it's not low density polyethylene, it's high density polyethylene. Rubber is, by this reaction, I take methyl 1,3-butadiene and polymerize it into rubber. But you can see as this electron goes over here and that one comes into there, that electron comes on into here and that one comes out to there, and it propagates the polymer and you end up with a double bond in the middle. I don't expect you to do all of these reactions. Here's polyadipic acid or nylon. You can come back and look at these. Here's tetrafluoroethene is going to make polytetrafluoroethene or Teflon. That's Teflon. So you take the Ziploc baggy kind of stuff, no hydrogens, all fluorines, and you got Teflon. I'm not a real fan of Teflon. I don't like non-stick surfaces. And you can see, you can go into stores right now, and they're moving away from Teflon non-stick surfaces because of the potential things that come off of Teflon onto your food. They're going to other non-stick surfaces other than Teflon. Yeah, so, but that's Teflon. I am a fan for it for putting it around pipes and making things slip real well and that sort of stuff, but trying not to get it close to my food. All right, now here's a neat little, if you looked at one of your drinking bottles, what you're probably going to see on the bottom of your drinking bottle is that triangle of one of these water bottles. You'll see a triangle with a number 1 in it. PETE. What is that? Polyethylene terephthalate. That's a very common one for drinking water bottles and that sort of stuff. This is polyethylene, high density polyethylene. Low density polyethylene. So here's your bread bag, sandwich bag, Ziploc baggies. Here is your milk and water jugs. Polyvinyl chloride, if you were a builder, a plumber, and you're running, instead of running pipe, you're running plastic pipe for water, hot and water, cold water, it's most likely polyvinyl chloride. It is an ethene, but it's got a chlorine on every other carbon. So here's your monomer unit right here. So the next one is going to have a chlorine and a carbon, and the next one is going to have a chlorine and a carbon. You see how that's repeating? That's polyvinyl chloride, PVC. And a plumber would say, we need 50 feet, 100 feet of PVC. 1-inch PVC, right? You've heard that? You've done that. Okay, that's it. That's what it's made out of. Polyvinyl chloride. Polypropylene, polystyrene. This is the big white sheets, or these are the little coffee cups when you need a cheap little coffee cup. Polystyrene, or the big 4x8 sheets that builders put on the sides of houses and insulate the house before they put the siding on it. This is the one you want to stay away from with your food. If you got plastic containers at home and they got that in a 7 on them, don't be putting that in your microwave or eating food out of it. Why? Because it's other. What's that mean? If it doesn't fit in any one of those categories, we throw it in there. And that's where polycarbonate goes in, and bisphenol A leaches out of polycarbonate. They used to make baby bottles out of polycarbonate, and that's been banned. So when you see the label that says no BPA, you seen that? Why is that out there? Because people said, I don't want BPA. Where's the BPA coming from? It's coming from plastics like that. Not all the time. That's other. There's a lot of stuff in that category, but that's one of them that's in that category. What?
BPA stand for?
Bisphenol A. And we should see, we'll come to phenol in chapter 12 very soon. Bisphenol A. BPA. That's what BPA stands for.
I think a lot of the baby
So it's an alcohol?
What?
It's an alcohol?
It was. I think, I'm not sure I could draw that right away, but it's two phenols, which are alcohols, but they've condensed on each other, so you end up with a carbon in between them. We'll
7 would have BPA.
yeah, 7 could, if it was polycarbonate. I'm just saying not everything with a 7 on it is polycarbonate. But I wouldn't trust anything with a 7 on it for food, and particularly going into the microwave, where it gets hot and this stuff can come out of it. All right, I'm not going to dwell on aromatics. I'm not going to dwell on polymerization. I want you to be aware of it. A question could come up, how are most plastics made? What reaction leads you to most plastics? Polymerization of alkenes is the way most plastics are made, by polymerizing alkenes. So you can see how important alkenes are. We're talking $1 trillion industry around the world making plastics. All kinds of plastics. Specialty plastics, very generic plastics like what we mentioned. Now let's look at aromatics. This is the third class in this chapter 11. It is unsaturated. Benzene is C6H6. If I start making a 6-membered ring, and if I put a double bond and then I skip one and I put another double bond, and I skip one and I put another double bond, I've got alternating double bonds in a ring. Now, if I look at that and I say, 1, 2, 3 carbons, how many hydrogens go there? 1. So there's only 1 hydrogen on every carbon. I mean, it's the same. 1, 2, 3, 4. 1, 2, 3, 4. Every carbon has a single bond on one side of it and a double bond on the other side of it. So it only needs 1 other bond. All right, so sometimes the line formula of that could be this. That's benzene. Or it could be written this way. Rather than just putting those double bonds around there, they just draw a circle in the middle of the ring. Those are all. So here's your structural formula. Here's an acceptable line formula. Here's another acceptable line formula for benzene. I don't expect you to go into this is just showing that you could put the double bonds there, there, and there, or you could put them there, there, and there. These are resonance structures, two acceptable structures that are both options for drawing the structure of benzene. So what is it? And that's what led to saying, well, it's probably something in the middle. It's probably something like this. It's not like you have a double bond there. These electrons are being shared between those 3 carbons. Those electrons are being shared between those 3 carbons. Those electrons there. So you you kind of have a dotted line or a 1.5 bond everywhere, and so that's what gave rise to just saying those electrons are delocalized. These are localized between those two carbons. We're saying all these extra electrons are delocalized, shared with all 6 of the carbons. And Kekel proposed this sort of thing, that you have a pi cloud. You have a cloud of electrons above the carbons and below the carbons, and it does give rise to a molecule that doesn't behave just like an alkene. You can't just come along here and say, oh, I'm going to react this with bromine and get a bromine on each of those carbons. It doesn't react like a standard double bond will. It's in an aromatic compound. Aromatics are always rings. They don't have to be 6 rings. They can be more than that. So let me go back to that. This does not just go the way we expected for an alkene. Overlapping orbitals. These are all acceptable structures. Okay, so benzene, this is chlorobenzene, nitrobenzene, ethyl benzene. It's got an ethyl group up there. This is a molecule you should, for chapter 11, you should make a 3x5 card of this and memorize that structure. Toluene. That's not an IUPAC name. That's the that is the IUPAC name and the common name. IUPAC came along and said, we're not going to give that any kind of new name. We're going to just accept the common name as the official name of that molecule, toluene. So people have trouble pronouncing it. Maybe I do too. Toluene. Toluene. So this is in chapter 11 right now, aromatics. This is in chapter 12. We were just talking about bisphenol A. That's phenol. It's benzene with an OH group on it. So that will be a 3x5 card, so for chapter 12. And then the others come in other chapters. So don't worry about all of these right now. Just worry about these as far as exam 1 is concerned.
Okay, so chapter 12 is all going to be chapter 10 and 11 and 12 will be all parts now.
Yeah.
And our exam is on Monday?
No, Wednesday, and we're in a crunch here because we got chapter 12.
Do you have a review out for the test?
Yeah, I got a bunch of resources put up there. Okay, probably 2 other things that you do need to grasp about aromatics. Can we stay 1 or 2 minutes over? Is that possible? I got a bunch of papers I could hand out to you. How many of you have a 12:30 class? Okay. We'll. Okay, this. Let me just draw this over here. What do we got here? We've got 1, 2, 3, 4, 5 carbons. 5 carbons, 2, 3, 4, and on the 4th carbon we have a benzene ring. Okay? So ignore the benzene ring for a minute. See that? I put too many hydrogens. So if I look at that 5, that's 1 pentene, right? You with me? So now on the 4th carbon, that's carbon 1, 2, 3, 4. On the 4th carbon, I have a benzene ring. Well, we don't call it 1 benzyl, we call it 1 phenyl. 4 phenyl, 1 pentene. So just keep in mind that this thing right here with a place to bond to a chain is a phenyl. All right, and then the only other thing we have to cover, someone help me. Here you go. Would you hand everybody one of hand those back. And over there. One.
Do you need anything else?
I have the chapter 12 homework, but I don't know how much good that's going to do you right now.
Chapter 12. You said you have chapter 12.
Yeah. Yeah, you want to give everybody one? Okay, you're getting 3 papers. Let's see if I can call this one up.